It's record. Yeah, it's recording. Okay. Hello, everybody. Today it's a pleasure to have as a speaker Sam Gralla from the University of Arizona, and he will tell us about the geometry of strong field electrodynamics. Please, Sam.
All right, thank you. So a lot of what I'm going to talk about actually goes back to, well, it goes back to the discovery of pulsars, people thinking about plasma physics in strong fields, but geometrizing it, a lot of a lot of the properties of the theory were first figured out in geometric terms by a fellow named Uchida, actually, in the 90s. And I got interested in this in 2014 with, wrote this paper with Ted Jacobson. Let me see if I can use this fancy technique. And then worked on and off throughout the years, and some recent papers here with my student Yang Kai, who's now a postdoc at the TD Lee Institute in China, and with a current student, Mori Mizuno. And so a lot of what I'm going to tell you was figured out by other people. I'm really only going to mix in a bit of what Mori is doing at the end, and if we have time, some of these papers. But I just want to take a tour through this subject with you and give an informal presentation. I'm just going to scribble some equations while we go through it. And especially since it's a small group, please just, unmute and ask a question at any time. I think this stuff is cool enough to demand your attention and simple enough that you can more or less follow it if you slow me down a bit. So let me start with why these kinds of strong fields occur in nature. And so what I want to think about is so some kind of strong electromagnetic field. And let's just imagine there's E and B. Let's not be too careful. For now, let's just say electric and magnetic fields are both present. And you can construct this parameter, which for some reason I call Xi naught. I think I got that from some laser physics paper or something. We're not going to do lasers, but what you do is you take the electron charge, the typical electric field strength, and the typical radius. So E is the fundamental charge. Capital E is the electric field. Typical strength, and R is some kind of scale of variation. And so this is like the voltage times the charge. This is a typical energy that a charge could be accelerated to. And you just divide that by the mass. So what is this thing? This is like how high typical energy of a charge, sorry for the scribbles, over its mass. And so this is interesting just because if you can get to a case where this is very large, so if this thing is huge, then what's going to happen? Well, and I put 3 greater than signs because, like near a typical pulsar, the order of magnitude estimate for this thing is huge. It's like 10 to the 16. Like it's not just very large, it's extraordinarily large. And so I really like extraordinarily large numbers because I don't have to think much. I don't have to know really anything about QED to know that some kind of QED process is going to turn on and have you make more electron-positron pairs because you just have so much energy, or you have 10 to the 16 times more energy available in a charge that got accelerated than you need, right? You need roughly twice the rest mass to make a pair. So the kind of cartoon idea is some QED process or other will make you pairs. So E plus, E minus. And so I'll kind of put a cartoon up here just to give you a visual. If I can figure out how to draw a circle. There's a circle. Nice. Let's add some text. So we'll call this a pulsar. And we'll move this over here. And so the pulsar is, well, it's rotating, and that's part of what makes the electric field out of the magnetic field, since it's a conductor. But what we sort of care about is there's like some kind of dipole field. And I won't get into the details, but these field lines start diverging. Formally, they open. And there's actually a current sheet here. None of this really matters for the talk, although we can get into it. But you want to imagine that what's happening is there's some, charge here that's getting accelerated to high energies by some E. So I'll code E as red and B as blue. And this thing is emitting some gamma ray, and there's some process like gamma. Gamma goes to E plus E minus, which you can think of the B field as photons. So something like this, and many people know a lot more about how this works than I do, but this is a cartoon for why you expect to have to deal with charged particles in strong electromagnetic field. The electromagnetic field is unstable to the creation of charged particles. So this is the backdrop for the whole talk. Any questions now? Okay. Now, something very interesting happens when you make your plasma by this kind of process. Let's think about the energy density in the magnetic field divided by the energy density of the particles. So let's do this. Energy density in the magnetic field divided by energy density in plasma. So this includes the rest mass when I say energy density in the plasma. There we go. So there's my ratio of these two things. And let's work out what they are. Not sure this is saving me time, but that was pretty fancy. So the energy density in the magnetic field, that's going to be B squared. Not going to worry about units here. And then the energy density in the plasma, that's really going to be the, I haven't worked out that yet. We have to figure out when this thing shuts off. So hold that thought. We have to figure out the mass density of the plasma here. Let me shuffle this equation down a bit. And let's work out, so how much plasma. So how's this going to work? Well, basically, it's the component of the electric field along the magnetic field that's accelerating the charged particles. So if you're a relativistic plasma physicist, this is very natural to you. If you're a relativist, one way to think about it is the Lorentz invariant is E dot B. And so if E dot B is 0, you could boost into a frame where there's no E and there's no acceleration. So it's E dot B that accelerates plasma, the parallel component of electric field. So basically, you're going to make charges until the new electric field cancels the order of magnitude of the old one, okay? So the way to think about that is the divergence of the new electromagnetic field, which, you can just think of as like E over R, has to be the old electromagnetic field. Well, it's like E over R. That divergence is going to make you a charge density that has to be sufficient to cancel the old electric field. Okay, so the typical rest mass density of the plasma is going to be rho is equal to this typical charge density. That density to screen the field. And then we just have to multiply by a mass to charge ratio to get the typical density of the plasma. So this mechanism not only produces plasma for you, it tells you what the typical plasma density is. And now we can take that and we can use it to compute the energy density of the plasma just by multiplying by the mass. So we won't even think about Lorentz factors. We'll just look at the rest mass energy. If we put them in, it doesn't change much because this number is so big. So we're gonna, did I do this right? Something looks, oh, it's already the energy density here because I put the mass in. Okay, that wasn't number density, that was energy density. So we just divide by this thing on the bottom. Oh. Wow, all right, my app is freezing here. Let's try that again. Okay, thank you, the world of cloud. Okay, there we go. So E times M over R times E. Okay. And now if you remember this other parameter we define, the last thing we have to say is my gosh, not really. No, thank you. Okay. And anyway, so we're thinking about this situation where there was sort of E and B in equal measure. Ultimately, that's because the pulsar is rotating pretty fast. You get such big numbers, these orders of magnitude don't matter too much. So we're going to imagine that E is like B. So we're going to put E squared in the top, make that a little thing. And then we still have E, capital E, M over RE. And so with technical delays and mistakes now corrected, we triumphantly get that there's an E in the numerator, there's a little e in the numerator, there's a big R in the numerator, and there's an M in the denominator. And you may recognize this is the same parameter we started with. This is this zeta naught. Okay, so when you have this zeta naught very large, you get energy density in the magnetic field over energy density in plasma. Well, by assumption, that was very large. Okay, so this this little order of magnitude calculation shows you something that's been, of course, known for a very long time and really is a foundational observation of the theory of pulsar electrodynamics, which is that these kinds of plasmas, so EM fields are unstable to magnetically dominated plasma in this regime. Okay, so any questions about this little order of magnitude estimate?
If I missed the beginning, could you just repeat what is the meaning of capital R?
That is a scale of variation of the electromagnetic field, which I sort of scribbled here in the indecipherable scale of var.
So if the scale of variation is, if it takes infinite distance, if the variation is very slow, then zeta would always be extremely large?
That's right. So the energy you can get...
a constant electric field.
Yes, and it's because constant electric field is very hard to make in nature. But if you can make it, you can get a lot of energy out of it, right? You just accelerate the particle, right? It's really the voltage that matters for how high energy a particle will become.
Oh, so it's some kind of accumulated effect of something like the total voltage.
Yeah, exactly. That's why this happens near pulsars, because they're absolutely massive. They're kilometers in scale, and they have these huge magnetic fields, and you get some electric field from the rotation of the conducting crust. And same for black holes. Excellent. Thanks for the question.
Sam, so small question. So the bottom inequality is, I mean, the bottom condition, the energy, this ratio between the energy density, the magnetic field, and the energy density in plasma, is that equivalent to the force-free condition?
Yeah, I'm going to move on to force-free now. So this is the order of magnitude estimate that says when you make plasma by this mechanism, you're in this magnetically dominated regime. And then where we'll get to the talk title, geometrizing things, is there's this theory called force-free electrodynamics, which is marvelously geometric. Okay. So that's a great segue. So let's do that. Let's ask, how do we model this in a magnetically dominated regime? Well, we have conservation of stress energy. So there'll be some stress energy of the matter and some stress energy, just the electromagnetic stress energy. That's always conserved, but I worked maybe a little harder than I should have to show you that actually the matter is negligible. Like even the mass of the matter is like negligible. The charge of the matter is really important. That's what got this whole thing started. The charge is actively screening the electric field and so on now that it's been created. But the matter is dynamically irrelevant. So you get to throw away this term. And so, it's this term on the left that gives plasma physicists nightmares. They have to deal with this. It's really complicated to model all those many charges, right? When we're dealing with this aspect of pulsar physics, we get to throw it away. And so what we find is that the stress energy of the electromagnetic field is conserved all by itself. Now, if you're used to thinking about vacuum electromagnetic fields with no charges, then this equation is pretty trivial. This is just automatically true. You can derive this from Maxwell's equations. But there's a little calculation that tells you that in general, what this thing is equal to is the field strength dotted into the charge current if it's not vacuum. Okay, this is just an identity. You can get it, if you like fancy stuff, you can get it from the action. Otherwise, you can just check it. It's just true because this thing here, the definition is del mu up to sine, So it's just, this is some f squared thing on the left. This is some f squared thing on the right. You use, the second Maxwell equation, move things around, and you'll get this identity. So what we're learning is that the theory of this magnetically dominated plasma is the following equation. Conservation of stress energy holds, but we rewrite it in terms of F and J. And let me plug in the definition of J. F, let's do it here. I don't know how I'm picking my indices. Oh no, I need to contract. Let's do rho nu equals 0. So this thing is the key equation of what is called force-free electrodynamics, because the left-hand side is the Lorentz force density. So what you're finding out is that in these strong magnetic fields, where the matter is there screening the electric field, but not important in terms of its mass, is that the Lorentz force density vanishes at every point in space-time. And believe it or not, that's a deterministic theory for the electromagnetic field. You can put this in evolution form, and as long as you're magnetically dominated, the b squared greater than e squared, not the other sign of the invariant, which we are kind of by a setup here, these are closed deterministic equations for the electromagnetic field. So you get this nonlinear field equation for the electromagnetic field, which reflects the presence of plasma, but it's not in your mathematical description. So it's like plasma without plasma, if you like. Okay, any questions? Okay. So you can study this equation on a computer. You can study it analytically, which people did in the early years. Even before they understood the full dynamical theory, they had stationary versions of this, and they were writing down solutions. 10, 20 years ago, the first numerical codes were doing this, and it was a big deal. I'm going to talk about studying it analytically with a geometric framework, so that's why it's going to be suitable to a relativity seminar. And at the end, I'll tell you what we're doing now with analytic approaches. This isn't quite published that I think will be useful for astrophysics, and I'll show you why. But for now, let's just enjoy this marvelous equation, beautifully simple, nevertheless accurately describes physics near pulsars and some black holes as well, and understand it in geometric terms. So the first thing I want to point out about this equation is just writing a little more abstractly as f dot j equals 0 here. What we see here is that this thing j, which we're going to assume is non-zero, so we're doing plasma. We actually have some current. This is a 0 eigenvector. It's sort of a physics way of saying, it's something you dot in, you matrix multiply with f as a matrix, and you get 0. So that already tells you that f is very special. So in the parlance of, I think in relativity and plasma physics, you would say f is degenerate. If you like principal null directions, it means, no, it doesn't in this case. Never mind. So f is degenerate. It has a 0 eigenvector. In fact, it has 2 0 eigenvectors because it's an anti-symmetric tensor. So there's 2 vectors, let's say such that f dot g equals 0, so f dot v equals 0, so 2 vectors in the kernel of f. So we have a subspace of vectors that annihilate f. Algebraically, you can check that this means E dot B equals 0. Otherwise, in the invariant form, that's F mu nu, F tilde mu nu. Sorry. Yeah. So that's good. That has physics. We should check in, right? We started this whole thing by saying charges would screen the electromagnetic field. Well, that would mean E dot B is 0. So we interpret this as complete and instantaneous screening of parallel electric field. So this diffuse plasma that that disappeared from the description because we don't model T matter, we sort of see that it is still there because E dot B has to be 0 for solutions of this equation. So that's a nice gut check on the physics. And let's go on and think a bit more about this kernel. So let's consider 2 vectors, capital X and capital Y, be in this subspace that annihilates F. So what that means, by definition, is that X dot F equals 0 and Y dot F equals 0. So this dot is just contraction with an index of F. And now let's do a little calculation. So the first thing I'll remind you about, people are probably familiar with in a relativity seminar, is the magic formula for the Lie derivative of a differential form. So F is an antisymmetric rank 2 tensor. It's a differential form. So we can take the Lie derivative of F and use Cartan's magic formula to write it as one term is x dot df, and the next term is d x dot f. That's Cartan's formula. And if you remember your Maxwell equations, this thing here, df, this is just the no monopoles Maxwell equation. So that is always 0, df equals 0. And then by assumption, this is 0 because of our equation here. By assumption, it's in the kernel. So any vector in the kernel has 0, or f has 0 Lie derivative around any vector in its kernel. And so f is really, you can integrate f to get the magnetic flux. It's really tracking the magnetic flux at a point. And this is sometimes called the frozen flux property. This is a sort of very efficient derivation of what in 3+1 language and with electric and magnetic fields takes some few pages to write out Alfvén's theorem. This is Alfvén's theorem of frozen flux. So anyway, that's sort of one property of the kernel to get at its nature. And let me show you one more. So now what I'm going to do is I'm going to think about the commutator of these 2 vector fields. So recall that the commutator of x and y of 2 vector fields is the same thing as Lie x, y. But I'm going to think of it as the commutator. So I'm going to do that. Whoops. So x and y commutator. And what I'm going to do is actually dot it into f. You'll see why in a minute. But what is that? Well, that's the same thing as the Lie derivative of x, y. That's now a vector dotted into f. And now the magic formula again. So that's what I'm doing. Oh, no, I'm just using the Leibniz rule, even better. So really what we're going to do is this Lie x is a derivative So we can write it as two terms, one which is Lex of y dot f. So since I got confused, you guys might too. So this is just the Leibniz rule. So Lex of y dot f, and then we have to subtract off the one that we didn't do. Lex, oops, I should say f. And, but I've assumed again that y dot f is 0. That's just by assumption. These are vectors in the kernel. And what do we have here? Well, we have Lexf, but I proved that Lexf is 0 already. That was this equation. Okay. So now I'm going to jump back to physics. I hope you enjoyed that little bit of math. There's a really nice interpretation here. Well, I need one more bit of math before I jump to physics. What I've shown here is that the commutator of x and y is also in the kernel. That deserves an exclamation point, right? So I've shown that x commutator y annihilates f in the sense that you dot it in. We're trying to understand this kernel. It tells you that the kernel is integrable. Okay, so that there are actually two-dimensional submanifolds. So the kernel is tangent, or kernel vectors, I guess is the way to say it, are tangent to two-dimensional submanifolds. And what are these manifolds? They turn out to be the worldsheets of the magnetic field lines. So if you think about the magnetic field vector, let me write that out. If you think about the magnetic field vector, it will always be in the kernel because, let's see, hopefully I can. So B is going to be what? F tilde UB according to some observer. And then if we dot, this better work, otherwise it'll be embarrassing. If we dot this in, we'll have F tilde, let's say B, C, UB. There should be a really simple proof that these are that the magnetic field is always in the kernel. Now I know from experience that this thing is in fact no, I'm not getting it. Did I include this in my notes? All right, I guess it's not obvious. If you use properties of degenerate fields, you can show that these two things are orthogonal, but maybe it's algebraic. So I'm just going to have to make some assertions. So basically, this F is proportional to a volume element on the field sheet. And this, where's my eraser? And this F tilde is perpendicular. So I didn't show that. That's disappointing. I was really hoping to give a talk where I literally showed everything. So if any of you notices a quick argument where I can prove this, let me know.
Let's see if we can understand the statement. The statement is for Lorentz free electrodynamics or all electrodynamics?
This statement relies only on two assumptions. df equals 0 and well, 3. And so degenerate, no monopoles.
So this means that E squared equals B squared.
Nope. So E dot B equals 0.
Okay.
B squared greater than E squared. This just makes the field sheets time-like. So they actually represent magnetic field lines. Time-like kernel. And this is no monopoles.
Okay. So in particular, for electromagnetic fields where the electric field is zero, usually we talk about magnetic field lines, and you're speaking of magnetic field planes, right? Even in flat space.
Absolutely.
So what? So the field lines are integrable, and we can take a family of lines, and we always get planes, no?
No, so it's each line. So it's actually easier to understand if you imagine a time-dependent situation first. Easier to understand why this is adding value. So take your zero electric field, but
what about constant magnetic field? Uniform and time independent.
So then so these are the world sheets of the magnetic field line. So then your planes are just, if each magnetic field line is in the z direction, then you have the zt planes. So it's the field line, but it's just stationary. So
so it's the ordinary. So if it's stationary, it's the ordinary magnetic field lines with t.
Yes.
Thank you.
Yes, and in fact, it's always, that's what I was trying to prove here. I bet there's a slick argument, but I can't come up with it live. It's always the ordinary magnetic field line. So the beautiful thing about this picture is, so magnetic field lines are great. They come with conserved magnetic flux, and there's a lot of intuition in plasma physics behind that, you know, tension and pressure and all that. But they are observer dependent. When you pick a different slicing of space-time, you get a different choice of magnetic field. Let me draw better. But these field sheets, when you have degenerate fields, these time-like field sheets really are observer independent. They give life to the magnetic field line. So you can imagine this is a field sheet, which is a world sheet of a magnetic field line. And then if you want to know about a normal field line, you just take any slicing. So if you're in flat space-time, maybe it's a flat slicing, but you know, you just sort of consider a time slice. So this is a time slice representing some instant of time. You know, and people who do black hole electrodynamics have some time slicing and talk about magnetic fields according to some family of observer. Well, this has some intersection with the field sheet, and that is going to be the field line according to these observers.
Maybe a general question, if we're at questions.
Yeah, please.
We're talking about the geometric perspective on this kind of electrodynamics. Is the geometric perspective dependent on having a curved space-time, or this could be also equally well in a flat space-time?
Absolutely. Yeah, I think it's just as useful in flat space-time. We have special relativity. We have, you know, different observers to play with. I think it's very valuable to develop geometric intuition there. It's also, I will make sure at the end to mention what we're doing with this now for astrophysics. The geometric perspective is also very useful for instantly identifying conserved quantities when you have symmetries. Now, in flat space-time, people have worked on this for 50 years, so they found all the symmetries. So it's gotten its value added in curved space-time, where we can immediately write down the symmetries that people haven't found necessarily. There's a few cases where they haven't been written down. But that's the real value added, because then with symmetries, you can do things analytically. And I'm going to argue that this analytics will help us with numerical modeling.
Okay, perfect. Because usually in GR seminars, we assume there is going to be an essential GR. Here, GR is not essential, but the geometry is essential.
Yes. Yeah, I didn't realize you wanted. I definitely could have given you some hardcore GR if that's what you wanted, Shahar.
No, it's okay. I just want to understand. I needed this clarification. I don't do any good physics.
Okay. Yeah, that's my point. I mean, I'm barely going to tell you anything I figured out at this rate, but I like it. I want to teach you guys some cool stuff. Okay, let's keep going. So let me give you some intuition for how we use this sort of thing in astrophysics. So Kurt Michael found a nice solution. So let's look at a force-free solution. And it's like this. So the field strength is B naught. These are just some parameters. B naught is the typical field strength. R is a stellar radius. You could combine these together into a parameter, but this is a nice way to think about it. And I'm going to write it as this sort of differential forms viewpoint. So this solves force-free. Again, Michael found this. Ted and I found some really cool ways of quickly deriving it, but it's his solution. And it's a great example for understanding these field sheets because we've written it in this form where you can see that on these field sheets, so remember the field sheets are the vectors that annihilate F. So when we write it in this form D of something, if we dot in something that is perpendicular to the level sets of cosine theta, then it's perpendicular to D cosine theta. It's in the field sheet. So on the field sheets, these two things are constant. So cosine theta equals constant, phi minus omega u. Let me just write t minus r. U is retarded time here. Phi minus omega u is constant. Okay. And so I included a cartoon of what's going on in this solution up here. Let me grab it and copy it, and we'll look at. So let's grab this one. All right, let's grab this one first. So these are the magnetic field lines. Whoa. Used to be faster at this in the Zoom era. Bit out of practice. So these are the magnetic field lines of this solution. And maybe I'll just re-grab it from my screen as opposed to attempting this scrolling thing. And here are the magnetic field sheets in space-time. So here what we've got is the equatorial magnetic field sheet. So let me write all that out. Equatorial magnetic field world sheets. And so you can see that the field lines themselves, so when we reckon them in a given frame, they have this kind of Archimedean spiral. So this on the right is a space-time diagram, and on the left is a spatial diagram. And okay. And so the field sheets, you can kind of see if you imagine slicing this thing, put vertical slices through it, you'll get those spiral field lines. But you can see that the field lines are rotating, right? As you go higher up, they're kind of rotating around. Actually, because it's a 2D manifold, there's ambiguities. You can identify different field lines at different times in different ways. But I think rotating is the easiest way to think about the time evolution of these field lines. And so there's rotating field lines in this stationary solution. Which when I first saw people saying this, it kind of threw me for a loop because nothing is changing. Everything is time independent in this solution. There's a t here in this potential, but when you take dt, it's just a component of the form. So it's this stationary magnetic field configuration. But in this sense, the field lines are actually rotated. And you can make that precise with this magnetic field sheet idea. And you can see it in these equations as well. If we change t here, keeping theta constant, we're going to have to change something else. So you can either change phi and think of them as rotating, or change r and think of them as expanding. Those are kind of the options. Okay.
What are the boundary conditions here?
Well, this is just a solution, so I didn't think of it as boundary conditions, but it's true that I drew a little sphere here. So this solution would be singular at the origin. So you're supposed to think of it as generated by a little conducting sphere. Going back to the cartoon of the pulsar, this would be a pulsar whose magnetic field lines are radial, so just sticking straight out of it. This is sometimes called the monopole solution. I don't like that term because it you know, no matter how many times I say I'm not doing fundamental monopoles, someone asks me about fundamental monopoles. So this is just radial field lines. It's just a place where you can have analytic solutions. Radial field lines coming out of the star. Okay. So in 15 minutes, let me give you some highlights of sort of what we get out of doing everything on the field sheet. So the sort of core, let's say, principle of our approach, formulate all physics. So let's say for pulsar or black hole magnetospheres, formulate all physics geometrically on the field sheet. The idea is these geometric structures are there. They're not just for relativists to gawk at and say, oh, it's so pretty, we're relativists, and so we like it, although I do that with a fair amount of my time. The point is to use it for something. Okay? And let me show you and try to get to the latest thing we're using it for. With Maury, my student, which is we are studying two-fluid plasma near pulsars and black holes. So this is with Mizuno, my student. It'll be out pretty soon. So core principle of our approach, formulate everything geometrically on the field sheet. First, let me tell you what the two-fluid theory is. So now we have two species, U plus and U minus. So these are the four velocities of electrons, positrons, anti-respectively. Nice, it corrected my P into a triangle. There's also the densities, N plus and N minus. So this is cold two-fluid plasma. It's sort of the simplest approximation that has two species, so you can get the plasma frequency and really get into the plasma physics. And they're going to satisfy the continuity equation, N plus minus U mu equals 0, and there's going to be Maxwell. Okay, and that's the two-fluid theory. So it captures a lot of plasma physics. And Sasha, oh, I forgot, I shouldn't act like Sasha was a very important co-author on this paper. He got lost in the rush to promote my students. So Sasha Filipov really helped in a lot of ways getting down to the physics. And, I got him to commit that, yeah, two-fluid captures almost everything about the pulsar magnetosphere, except for local stuff you could do with full particle and cell codes. So that's a very good reason to study these equations. And we're going to study them in the nearly force-free limit, because for pulsars, they really are nearly force-free. This is the correct regime. And we'd like to get some mileage out of the fact that they're nearly force-free. We don't want to have to solve them exactly. So how do you do a nearly force-free limit? Well, the simplest thing to do is take the mass to 0. It's just the simplest kind of formal perturbation parameter. And it's just in recognition of the fact that if we scroll up, this is the same as B goes to infinity, which is really the relevant limit for a strong field magnetosphere. Let me briefly scroll up and we'll just look at the kinds of small parameters. We had ER over M, but E is like B, so EBR over M is going to be giant. So we could do that by just formally making M go to 0. That's the easiest way to think about it. If you've thought about gyro radius type stuff in guiding center, this is the 0 gyro radius guiding center approximation. We're not worried about any kind of circular motion, because in these fields, it's just instantly radiated away. All of these charges near pulsars are just stuck to the field line. In fact, they're on the lowest Landau level. It's really a quantum description. So we're going to let m goes to 0, and we're going to expand everything. I forgot to add Lorentz force law. So you need the Lorentz force for both plus and minus. And let's think about that one first. So, whoops. So m, let's write it as a mu plus minus. The acceleration of the plus minus ones is going to be plus or minus e f mu nu u nu plus minus. And let's think about what happens when we send m to 0. Well, the left-hand side goes away. So at 0th order, we have 0 equals f mu nu u nu plus minus. And that's just, again, the statement that f is degenerate. It has a 0 eigenvector. So we get these field sheets. And in fact, it goes further than that. F is going to be actually force-free. To see that, we have to remember that we can construct the electric current, J mu, from the positron current. So plus the electron current, U minus, should have been a same index on both sides. Okay, and so if f dot u, so if we dot this equation with f, then the left-hand side is f dot j, and the right-hand side vanishes because f dot u plus is 0, f dot u minus is 0. So it's force-free. So this is the regime we wanted to study by letting the mass go to 0. So this is really just a sanity check that this regime does arise. So this is nearly force-free. Now let's do the first order correction. So in m as our expansion parameter. So now we're going to have m a that will show up, except this a is really the 0th order, right? Because remember, m is our perturbation parameter. So the perturbation parameter appears in the equation. So the left-hand side has a 0th order quantity times the perturbation parameter. And then on the right-hand side, f dot u vanishes in the background. So I'm going to get two terms. I'll use a delta for perturbation. So I'll get that term. Let's do it this way. And plus f mu nu u delta u plus minus nu. And what we're going to do is we're going to project this equation onto the field sheet. So that was our principle, that everything we study, we want to think about geometrically on the field sheet. I had it in purple, so I better be consistent. Purple, project onto field sheet. So we dot with some vector on the field sheet. Let me not introduce the field sheet metric. I don't know. Just imagine projecting. What's going to happen when we do that is this is good. Whoops. Oh, come on. F. Sorry. Okay, when we project onto the field sheet, this term is going to go away. Because if you remember, the field sheet is the set of vectors where f dot v equals 0. Okay. So that's great because it decouples the first order equation. This thing just becomes pullback of F. We're just going to write it as pullback of F because that's what projection means. So I'm going to write that as pullback to the field sheet. And then nothing happens to this side because this is already on the field sheet. It's the 0th order F, right? The 0th order F, 0th order U, excuse me, already satisfies this equation. And so we're going to find out that these particles actually obey the Lorentz force law in the field sheet. Now, I've actually never seen anybody say this. So nearly force-free particles obey Lorentz force law on the field sheet, a two-dimensional Lorentz force law. I think we're going to be the first people to say this in the literature. I wouldn't be shocked if we discover, like, in some obscure Uchida paper from the 90s, he knew this. But I think this is just amazing and super cool. Like, you get an incredible simplification. If you go to Van der Voort or Kruskal, people this kind of guiding center approximation, you'll see this equation. And then you'll see like 10 more steps where they convert it into a huge, I'll say mess, with all due respect, of gradients of magnetic field, gradients of gravitational field, if there's gravity, all kinds of complicated terms to get the equation, which is actually just the Lorentz force law in the field sheet. So the geometrization conceptually gives you a new interpretation and makes the equation way, way simpler. Now, we'd be really happy if we could also use this in practice. And I will just assert, since we don't have too much time, that there's a paper coming out where we'll give this little argument. And we'll also show in practice how to use this. And so the real advantage of having this geometric formulation is it's very easy to spot conserved quantities. And so what Mori shows in this forthcoming paper is that in this two-fluid framework, from some very similarly short and elegant derivations, that there are two conserved quantities. All right, we'll be in purple now. One we're going to call gamma, which is U A plus dot chi A, which is going to be a killing field tangent to the world sheets of the magnetic field lines. Gratuitous to use different index, but fine. So these are constant on the field sheet. So chi is a field sheet symmetry. So what we mean by that is the Lie derivative of the field sheet metric. Well, since I didn't introduce that, let's just say it's a killing field. So Lie chi F equals 0, Lie chi, oh my gosh, Lie chi G equals 0, and Lie chi N equals 0. And everything is independent. So it's just, everything is independent of the symmetry, and it is tangent to the field sheets. Okay? And this comes up in rotating magnetospheres. The example to keep in mind in a stationary consideration field like Barak was talking about, that would be just d by dt. In a rotating magnetosphere, it would be dt plus omega d phi. It's a kind of co-rotating symmetry. So anyway, a couple lines proves that this is conserved. A couple more lines proves that these are conserved. So it's the field sheet volume element on the field sheet. And it gets dotted into something I'm calling capital J and chi B. Capital J is a cool thing I was hoping to tell you about. I've also never seen anyone write this out explicitly. Here's where the magnetic flux idea really, so the four-dimensional conserved current is NU. The 2D conserved current on the field sheet is per unit magnetic field, which you can think of as each field sheet being thickened into a flux tube and actually behaving like a wire and carrying a current. But I don't have time to explain that. just wrap up here by saying that now that you have these two conserved quantities, so you have two conserved quantities, it turns out they determine everything about the flow. The full nearly force-free solution is analytically determined by choosing these conserved quantities. And so here's our proposal for astrophysics, which is the next step after we write this paper. The idea is, first, you find a force-free solution. So this is for modeling an actual black hole or pulsar magnetosphere. So this is easy numerically these days. This is a, give a student a code, have the student figure out how to run it. Okay. Then what are you going to do with that? Well, you have to solve for these two conserved quantities somehow. And so what you do is simulate the small regions where charges are produced. So remember at the beginning, I told you there's this instability that makes charges, right? Well, those charges, when they're made, they're going to fly away. They're going to be flung outward by this magnetosphere. So something is replenishing them. So these are gaps. And so this is 1 + 1, or local. Let's just say local particle and cell codes. All right, so not a global particle and cell simulation, a local one. And then from 2, we learn about how the conserved quantity, or let's just say learn the conserved quantities. And we use these to solve for the flow everywhere. So I claim, and of course we haven't done this yet, so maybe we'll find that, that it doesn't work for some reason, but I see no reason why this shouldn't work. I claim this is going to be fully equivalent to a global peak simulation, which is what everybody is doing. So for those who don't know, peak is particle and cell. It's just following a bunch of particles like an n-body simulation. And, you'll notice that there's the only global solution is force-free, which is quote unquote easy. We just replace the global peak simulation by a local one that fixes physics, and then everything else is done quasi-analytically, at most having a sort of numerical representation of the force-free solution, and then, solving algebraic equations in that numerical representation. So I did my best in an hour to teach you a bit about the basic physics of pulsar and magnetospheres, show you how it results in a theory of plasma physics that is way simpler than any other theory of plasma physics, tell you a bit about the geometric picture, and show you how we're using that to really formulate a new approach to modeling actual pulsar and black hole magnetospheres that I think will have significant computational advantages. Thanks for your attention.
Thanks, Sam, for a very interesting talk. Any questions? So I'll start. So do you see this last method that you described as a reformulation of the theory of force-free electrodynamics, or do you think this?
No, this is the study of nearly force-free magnetospheres. So I didn't mention the theoretical motivation. I have this whole other theoretical motivation for studying force-free, which is that, for a decade, I studied force-free, and I said it's a universal limit of plasma physics. Like no matter what your plasma is made of, it reduces to force-free, and isn't that amazing? And if anyone ever asked me what's the small parameter that controls the validity of the approximation, I would say I have no idea. So theoretically, I just wanted to study an actual theory of plasma physics in the force-free limit and how you put the plasma back in for that particular theory. So that's what we're doing here. We're taking the two-fluid theory, we're studying it in the nearly force-free limit, and we're showing how you can systematically recover everything about the two-fluid solution. So that was a theoretical motivation, and then in practice, the idea is, well, this is easier than actually solving the two-fluid fully in this regime. You use the small parameter to your advantage.
Any more questions? So, well, I mean, do you think somehow this geometric picture could provide a way to reformulate? So without bringing the plasma in, but just for the plain FFE.
Oh, I think I'm done trying to reformulate that. I mean,
okay.
We you know, Uchida was already doing it geometrically. Ted and I added a little bit to that. And then over the years, I've explored all kinds of crazy other versions. I have with Nabil Iqbal, a string theorist, I have an EFT of strings version of force free. I have a bosonization paper where I did I've tried so many ways to reformulate force free. You know, this one is really just let's accept it in this, you know, really going back to Uchida and try to perturb away from it. But I'll probably perturb all those other formulations too. I always learn something.
Cool. All right. Any other questions? If not, let's thank Sam again. Shut off the recording.